Hello, my name is Angela Forcino, and I'm a Product Marketing Manager here at Ansys. On behalf of Ansys, I'd like to welcome you to today's webinar, Get the Highest Quality for Optical Material Data. Before I introduce today's presenters, let's go over a few housekeeping items. First, all callers have been muted to prevent background noise. Today's event is being recorded. You will be able to view the recording in about a week's time on the Ansys.com website. Simply select the Resource Library button located in the menu at the top of the home page. If you have any questions, please submit them using the chat box. While we will not have a question and answer session at the end of this webinar, we will be following up by email on any questions that are submitted. We will control the movement of the slides. Some slides are graphic intense and may take some time to advance depending on the speed of your connection. Okay, at this time, I would like to introduce our presenters, Matthew Reynaud, Senior Product Manager at Ansys, and Volker Schumacher, Managing Director at Opsira. Matthew joined Ansys 13 years ago as a consulting engineer. Prior to Ansys, he worked at ST Microelectronics, where he filed 7 patents. During his career, Matthew has led high-end photometry and visual ergonomics projects and is an expert in real-time photometric simulation, real-time rendering, and virtual reality. He holds an engineering degree in laser and optics and a master's degree in photonics. Volker is the general manager and co-founder of Opsira. He has served in this role since 1999 and heads up the Optical Design and Measurement Services division. Volker is continuously involved in the development and improvement of scattered light measurement technology and scattered light modeling at Opsira. In 2009, Volker won the Scientific and Engineering Award of the Academy of Motion Picture Arts and Sciences in Hollywood for his optics development of the film floodlight Aramax 1812 reflector. Welcome, Matthew and Volker. Take it away.
Thank you, Angela. So I'm Matthew Reynaud, Product Manager on Speos. I'm happy to welcome you to this webinar on material properties. On today's topic, I'll have a brief introduction of what material properties Speos can handle, what kind of complexity in an optical property can be obtained and simulated through Speos, in terms of different means of modeling materials. And in the second part, I'm happy to have today Volker Schumacher, Director of Opsira, to co-host this meeting and present different ways to correctly model and capture these optical properties, and in order to render it as best as possible through a Speos simulation. So, without further ado, let's dive into optical properties, and mostly for optical properties, BRDF. BRDFs are what we commonly use in simulation for characterizing the reflection of the light on the surface. The meaning of the BRDF is typically a distribution of reflectance, which depends on the incidence of the light hitting the material, but also depending on other factors like the wavelength, typically the color of the light, but in its physical description, that is the spectrum. And eventually the anisotropy, which means the orientation of the sample on which the light is going to hit the material. That's the essence of how we characterize optical properties through an optical simulation. And we have different ways to represent this. Either we represent it as a conoscopic map. For one known incidence, we represent a full capture 360 degree of where the light is going to be reflected and with which intensity, giving this total distribution. Or another way, which is more dynamic, is a 3D distribution function, where you can see the shape, depending on the incidence of the light, the shape of where the light has the most probability to be reflected, depending on its absorption, depending on its spectrum, depending on the orientation of the sample. So a BRDF, there are typically two main ways of having a BRDF into a simulation software. The first one being analytical, so rely on mathematical model to represent the distribution of the light being reflected on the material. The second one being relying on the measurement, having a sample, get it measured through a photogrammeter, and use this measurement in simulation. Analytical measurement, so you need to fit on a mathematical model, but there are many mathematical models with advantage and drawback as well. In many cases, you've got to find the right model that fits the material you need to model. Many models are what I call 2D model. Actually, when you consider the incidence of reflection of the light, you may consider the reflection as a circular symmetry, but very often it is not. So you need an advanced model to be as close to reality as possible. And also, not every model are physically based. By physically based, I mean the reflection has to be positive. Positivity means at any time the absorption cannot be below 0%. That's linked to energy conservation, which means the amount of energy that hits the samples wherever it's reflected has to be consistent together with the absorption of the sample. And the Helmholtz reciprocity, which is a principle that means that if I use this material in simulation, hitting the light with a ray of light and computing its intensity in a certain direction, if I make the opposite calculation considering this incidence of reflection, I should be able to retrieve the amount of light that has been incident. So it's a lot of consideration to have. Mostly in Speos, we generally rely on measured BRDF. And I would say even measured 3D BRDF, where we don't consider the reflection of the BRDF only in one plane of incidence, but in 360 degrees for each incidence, which is much more accurate, which tends to be compute heavy, but which is very well considered in Speos. That's why it's our basic format. And so in a measured BRDF, you've got a full copic capture. So per incidence, you've got the whole 360-degree information. The accuracy of this, while the model is completely free, the accuracy it's as good as the sampling for the capturing of the BRDF. So there comes the importance of using a good capturing system. Important also the accuracy at low angle. That's where the light is hitting the sample at low angle. That's generally where the mathematical model are getting less close to reality. And that's where measurement at least is representative of the reality. And as well, it's by essence physically based. As we integrate all of the energy of the light, we can check that it is captured and balanced homogeneously and respect all of these three principles. Now, looking into details, what a good BRDF can be. There are some aspects that can be captured as well. I've talked mostly about intensity distribution. Second part is spectrum for the color, basically. We capture the spectrum in order to see behavior like white specular reflection. I mean, when you've got a metallic reflector, you may have the color of the reflection of the specular reflection, which is basically this white square here. If it's a metallic mirror, you may have this reflection colored, but if it's a dielectric material like any plastic or any coated material, you will have the reflection white, even though the absorption of the rest of the material will be colored. So if you are considering the spectrum for every incidence of your capture, that's the kind of effect that can at least be represented through simulation. Another aspect of capturing the spectrum through the BRDF, that's pearlescent or iridescent material, like this example, where you can see the color is changing depending on the incidence of the light. See, this one is green with a tint of purple depending on the incidence. Or if I I have an example here. I'm not sure I'll get it on the camera, but typically lighting this sample will turn it from purple to yellow, depending on the incidence of the light as well. Then another very important aspect about having a spectral characterization, and here I'm rather talking about spectral characterization against RGB, red, green, blue characterization, because red, green, and blue are enough to capture the color, but to get the correct optical behavior, you need the full spectrum. An example here about alexandrite, which is a very particular stone with a very particular absorption spectrum that makes it a different color depending of the kind of light of the spectrum of the light that lights it. Typically, if I lit an alexandrite with a fluorescent light, like this one, with a very straight line spectrum, it will look like blue material, while if I lit it with a black body white, even if it's the very same white between those two lamps, because it's not the same spectrum behind, the appearance of the material will differ. That's the principle of metamerism. That's very important, especially if you've got parts of different materials, but you need the same color. This color has to match under different lighting. And that's something that you can predict only if you're relying on spectral measurement. Another particularity with anisotropy, which is typically a brush material. Anisotropy depends on the orientation of the material itself. If it's a brush metal, typically, if you lit a brush metal with a point light, you will see a straight line appearing, and this straight line will follow the direction of the brush depending on how you orient the material on the geometry. So in Speos, you have the possibility to orient this anisotropy thanks to texture mapping. And in terms of aspect of the BRDF, this is a kind of shapes that is given. That's very difficult to obtain analytically, especially when you see this shape, which is not elliptical, but getting a kind of a banana shape, which is the actual behavior of a true anisotropic, a true brushed material. Another important point for high quality measurement, high quality BRDF, it's the dynamic. It's the difference. The dynamic, it's the difference of the maximum level of energy that is measured and the minimum level of energy reflected that can be measured. Having this kind of wide range is very important, and the best example to illustrate this is a piano black material. Here you can see in this material, between the spectral reflection of this white spot and just next to it, the Lambertian, the diffuse reflection of this spot, there is an order of the magnitude of 1 billion. So it means between this spot and the darkest, I've got 1 billion. I need to, on the representation of the BRDF, I got to zoom a lot in order to be able to start to see the Lambertian, the diffuse part of this material. In simulation, it's very important, especially for coating. Here, another example, not this one, not on a specular, but on a very diffuse material. Taking black, the difference on extreme blacks, taking a standard black felt, it's very black. It's absorbed nearly 99% of the visible light. And to be compared with the Vanta black, which is one of the reference there, but absorbs more than 99.9% of the visible light. Knowing it is black is fine, but when you are working on stray light and trying to capture as much light as possible, what is important is not the amount of light that is absorbed, but the amount of light that is not absorbed. And that's where, through an accurate measurement, you're able to see how much light and how this light will be absorbed and not absorbed on the material. And so a high quality scanning system can achieve this and deliver through the simulation, deliver correct behavior on using one or another material for absorbing stray light. more aspects, because BRDF, many aspects of BRDF can be captured and restituted and obtained through simulation. Considering not just reflection, but also the transmission. So BRDF, the R stands for reflection, but transmission can occur. And when we capture both reflection and transmission, we call it a BSDF. We generally do this for this kind of capture for thin film and diffuser or coatings. If you need to blur out some lighting or have a certain coating to split colors on a surface. Rough surface, that's when you go into molding, you've got several levels of abrasion. Depending on the abrasion in your mold, you will end up with different effect, different blurring effect on your surface. Retroreflection as well. That's when you've got material, especially used for road sign, road marking in automotive lighting. When you've got some cathode optic or micropearl aspect on the surface, the light will be reflected back to where it comes from, and this can also be assessed and obtained through and retranscribed through simulation. And also asymmetric properties. When you've got a thin film with different properties on one side and the other, it's possible. And so if you revert it, the property will be reverted as well. That can be also measured and reused through simulation to match with reality. I've been talking about surface, but surface is not the only properties that Speos is known to simulate. The other aspect is volume property. So that's how the light will behave inside the material. Two major properties that happens when the light is propagating inside a volume. First one is absorbing part of this light. So that's what is making a material more and more opaque through the distance the light is going to travel through. If you look at this picture, that's a gray material, and so the thicker the material, the more the light is getting absorbed. And it's the same principle for volume tint. When you've got your the color directly in the bulk of the material, it's actually absorbing one part of the spectrum of the light, depending on the tint that is inside the material. And so that's where you can see the clear difference between a volume tint that is embedded inside of the volume and a surface tint where you have only a coating that is absorbing part of this spectrum. And the second main properties that can be measured and simulated in Speos is volume scattering. There we are not only considering the amount of light absorbed, but all the light is going to behave inside the material or hitting the particle inside the material. The light is going to be scattered and how it then exits the material. So that's what's giving a material a milky aspect, and that's what's making this material actually not something opaque, but something transparent. And depending on this transparency and depending on this volume scattering, characterize how much my point light will be spread through this thickness of material. And so again, when it's not tint, it's a milky aspect in white, but the real behavior is spectral, and so the material can absorb part of the spectrum of the light, giving a different color tint depending on which part of the color is absorbed and scattered through the medium. So if you want to know more into details about the material format in Speos and how to make this format, we have a couple of additional information you can access through these links, either on surface format, what is the format of BRDF and BSDF for Speos, and how you can make this on your own. And also we have more information on volume format, either for transparent non-scattering files or for more advanced volume diffuse materials. You can reach this link to get more information. And then if this is still too complicated, the best way to get the most accurate material for Speos is to go through an expert in measurement. And that's where I give the floor to Volker and his presentation of his company Opsira.
Okay, thank you very much, Mathieu, for this very good overview about doing this simulation in Speos. And welcome to this webinar. I'm Volker Schumacher, Managing Director of Opsira, and want to talk a little bit about scatter measurement and scatter modeling. First of all, I will give a short introduction to Opsira and then introduce to you our scatter measurement system and talk about scatter measurement techniques and post-processing of measured data for surface scatter measurement and volume scatter measurement. Opsira, we are working in the field of optical system technology. We give engineering services to customers, to optical systems design for illumination optics and imaging optics. We have a light lab where we can perform optical measurement for scattering measurement, luminaires measurement, and light source measurement. And we have test systems, or goniophotometers, spectrometers, and spectroradiometers, and luminance camera. Opsira was founded in 1999. We are a team of 20 colleagues, have 6 light labs, and more than 2,100 projects which we did in the last 25 years. And we have the Ansys partnership since 2021 for BRDF measurement services and BRDF goniometers. Our scatter measurement systems, we have 2 types available. There's on the one hand the in-plane goniophotometer. This is mainly used for volume scatter measurement. And then we have the 3D goniophotometer, the Gonio 2π BRDF for surface scatter measurement and volume scatter measurement. The in-plane goniophotometer, Gonio 2π 0π BRDF, this is a one-axis goniometer. We have here the sample, and here is the detector. The detector surrounds the sample, and the sample will be illuminated from a light source, which is mounted here. We have collimated light, which goes to the sample, and then it's scattered on the sample, and the detector surrounds the sample. It measures in transmission, and it also measures in reflection. On the side here below, we can see a transmission measurement. It's one type of material, but with 2 different thicknesses. The blue curve is 1 millimeter thicknesses, and the reddish curve is 2.8 millimeter thicknesses. For the 1 millimeter thicknesses in transmission, we see still some non-scattered light, and here we see the remaining part of the scattered light. For the 2.8 millimeter thickness, we only see a very low amount of non-scattered light, this one here, and this is all scattered. This is reflection, and this is transmission, and here we see the reflection. And sure, for the reflection, we have a very high specular peak from the surface, from the polished surface, and then we see the reflected scattered light for the 2 thicknesses. That's the in-plane goniophotometer, and then we have the 3D goniophotometer. This is a 4-axis goniometer. We use in our goniometers high precision drives. There are servo drives with a very high internal accuracy. Also, we are able, based on the setup, to make a very high angle of incidence. We are very free here how we can bring the light to the sample, and also in respect to the measurement. We can measure to very high angles and get only a very low edge shading. The principle is like we can see it here. The light will be come from the below side. It goes up, it's a collimated light. It goes up to that redirection mirror. This redirection mirror brings the light to the sample. The sample is mounted here. The sample itself can be rotated about on his own axis. And here is the detector, and the detector can surround the sample and measure the scatter characteristic. We have a very big sample holder. This makes this very flexible in the sample setup. We can here see the sample holder, and here it's a sample mounted to this sample holder. Like I mentioned, the sample holder itself rotates the sample if needed. Also, we can choose variable measurement resolution for different regions. Here we see a result of a measurement, and where we have the specular peak here in that area, we choose a high resolution, a high angular resolution, and where we have the scattered area, there we choose the low angular resolution, and so we have not to have so much measurement points. And this can be freely chosen for every angle of incidence. In respect to light source option, we have different light sources available. All light sources are fiber coupled and collimated light sources. We have available laser light sources with different wavelengths, from short wavelengths to long wavelengths. Also, we have LED light sources, and we have halogen and xenon broadband light sources, which we can bring up to that machine. In respect to the detector options, we have mainly two detectors available. There is a high dynamic CMOS-based detector. This has a dynamic range of up to 11 decades and a typical angular resolution of plus minus 0.15 degree, full width half maximum in combination with an LED light source. Here we see the signature of the machine. We go up from 0 to 11 decades. This is a logarithmic scaling, what we see here. And here we have a very narrow full width half maximum characteristic. Further, we can mount a spectrometer or spectroradiometer to the goniometer. Here, the dynamic range is a little bit limited in respect to that sensor. Compared to that sensor, it's still 8 decades, but then we have the result spectral resolved. The typical angular resolution is a little bit higher, with 0.25 in combination with a broadband xenon light source, what we have to use for this. Also, I want to mention some words to spectral measurements. We have two options for spectral measurements. There we can mount to the spectrometer to go to the goniometer, and then we get the spectral resolved scatter characteristic. Here we can see a result of volume scatter material measured at different wavelengths. We see the bluish curves, they belonging to short wavelengths. They are scattered more than the longer wavelengths here, the reddish curves, which has a lower scatter characteristic, a smaller full width half maximum. This is a result of the spectrometer on the gonio photometer. And also we do measurements with the spectrometer with an integration sphere, where we can measure on the one angle of incidence the transmission spectra and the reflection spectra. And based on that data, we can also calculate, an example of transparent materials, we can calculate the absorption coefficients of materials. I want to talk now about surface scatter measurement techniques. So in principle, we see three different techniques for surface scatter measurement. On the one hand, we have pure reflective materials like reflectors, like we see it here, bevels, dashboard materials, and so on. Second, we know transparent materials scatter on thin components like diffuser foil, diffuser films, or cover plates, where we have surface scatter on. And then we have 3D components like microstructures on light guides, microstructures on lenses. All these three different things has to be handled in different ways. The most easiest one is your reflective materials. There we can use directly the sample for the measurement. We have here a sample with a surface characteristic. It's only working in reflection. Here is the scatter structure on that component, and we illuminate the sample under different direction, different angle of incidence, from a small angle of incidence to very flat angle of incidence, and then we measure every time the hemispherical scatter in reflection. If there is some anisotropic effect, then we are rotating the sample. We see it here. Here we have a wider scatter characteristic, and here is a more narrow scatter characteristic when the sample is rotated. And for this, we have the sample holder, which can be rotated on the BRDF goniometer. So that is for reflective materials. Transparent materials like diffuser foils or films, something like we see here. You can see here individual LEDs, and if there is a diffuser foil in front of it, then it will be scattered and homogenized. So also this component can be directly measured. We have this sample with scatter structure on one side, and maybe on the other side it's a high polished sample, and then we are illuminated this sample from one direction and from one side and measure the scatter in transmission or in reflection. If in your application will be light traveling not only from one side, but also traveling from the other side, sure, here can also be then the measurement from this side, and then it will be measured in reflection and also in transmission. And so we have the complete information, the incidence from this side, reflection and transmission, and the incidence from the other side. And this results finally gives us such a Speos BRDF 180 model. Then third, we have scattering structures on 3D components like light guides or lenses. Those structures are a little bit more complex to measure, because we want to isolate this scatter structure. And for this, we are using a hemisphere, a high polished hemisphere. This is optical attached via immersion oil to a sample. Here we have the sample, here we have the structure. And we want to know how the light behaves if it travels to this structure. And we all not want to know not only under a small angle, but also under a very high angle, under angles where total internal reflection can occur. And that we can measure this effect, it's necessary to have this hemisphere. And that gives us the possibility to have very flat angles and shine under very flat angles to that structure and measure here in reflection and in transmission. We can also do it from the other side. Also here the light comes from air, and it goes via the microstructure, via the scatter structure. It goes to the substrate sample, and also we measure transmission and reflection. And again here the light comes from the substrate, and it will be measured in transmission and reflection. And this gives us the possibility that we can, based on measurement data and then a model of such measured data, we can, in example, define a scatter characteristic, in example, on a light guide, where the light travels to the light guide and comes on the flat angles to this structure. Some words to post-processing of surface scattered data. We have on the left side the measured data from the goniometer. we see some artifacts inside here. In example, there will happen some shading of the light source, which we will see here and there. And also we have some slight scattered angles, very high scattered angles on the high angles, which will be shaded from the machine itself. And we are doing via the Opsira BRDF converter. This is our program. Here we are doing interpolation of the data and the extrapolation of those data in the edge area. And also we make the artifact illumination. And after this conversion, we have the Speos anisotropic BRDF data available. This data can be brought into the Ansys Speos interpolation enhancement tool. And here it's the optimized file format as the result later. And though this file goes into the simulation in Ansys Speos. And the same is valid for Ansys CMix. And we see here a black material, and we see also here some specular effects here and there. And this happens on such a black material on the very flat angle of incidence. There, this material becomes more and more specular. And all these data are integrated in the measured data. This is for surface scatter characteristic. And also I wanted to talk a little bit about volume scatter measurement. In most of the cases, the information of in-plane scatter measurement data is enough. So that means we need only one cut in transmission and one cut in reflection. But here we have we are measuring normally on different material thicknesses. Normally 3 thicknesses are best, ideally. Number 1, a very thin material where still some unscattered light will passing through the material. Number 2, some material thicknesses as thin as the later application. And number 3, a thicker material, maybe as thick as the later application. And often it's not all of the thicknesses available, and then we are using what is available for that measurement. For the surface characteristic, it's very important that the surfaces are flat and that the surfaces are polished, because we only want to see the effect of the volume scatter characteristic, and we don't want to see the effect of the surface scatter characteristic. So it should be a polished surface that the only scatter effect will be created from the volume. When we have done this measurement, here we see again the example of before, a measurement of one type with 2 thicknesses in this example, in transmission and in reflector. Those measurement data we are doing in the post-processing, we use the Speos Excel macro. This is a macro provided by Ansys, and this macro uses the Speos in the background. And here we are able to introduce the volume scatter parameters of, in example, Henning-Greenstein or Gegenbauer. Also, we can bring in absorption parameters. And when we have a set of parameters, we can start a simulation of Speos, and this simulation delivers back some fault values, and also it delivers back some result of the simulation, and this can be compared with the measurement data. We see here the dotted line is the black one, is the measurement or the measurement data, and the red line is the first set of data which we have here. The green line is the second set of data, which we see there. And the purple line, this one here, has a very good fit to the measured data. This is the third set of data. And this seems to be nearly perfect, and this data can then be transferred to a Speos.material file, and this can be used in optic simulation in Speos. I also want to give a short outlook to the post-processing volume scatter data. We are working actually on an automatic volume scatter converter that will be soon available, and this creates automatically the Ansys Speos and CMake material file format. It means you have not to do manually fit to that. This works with this converter as soon as it is available automatically, and it defines automatically volume scatter parameter like phase function and mean-free path length, and also the absorption coefficient. So that's from my side. Thank you very much for your attention, and I would be happy to come in contact with you. This is my person, Volker Schumacher, and this is my colleague and partner, Jürgen Weishaupt. I'm happy to get contacts to you. Thank you very much.
That is the end of our presentation today. Thank you, Matthew and Volker, for this informative webinar on getting the highest quality for optical material data. As mentioned at the beginning of this webinar, we will be following up with any questions submitted in the chat by email in the next few days. Before we end today's session, we'd like to tell you about some upcoming events and introduce some additional resources. First, we are very excited to announce the Ansys 2024 R1 release. Ansys Optics continues to push the innovation envelope to deliver accurate, high-performance simulation capabilities for optics designers. The 2024 R1 release provides powerful capabilities that speed up the time to result, improve simulation accuracy, and expand interoperability with other Ansys products. Join us on February 14th to hear all about the latest feature updates in Ansys Numerical, Ansys Speos, and Ansys CMake from our team of optics and photonics experts. You can register today by scanning the QR code on this slide. Are you looking for an application example for stray light analysis for a smartphone camera, or a diffractive metal lens design example consisting of cylindrical nanorods? You'll find these examples and many more in our application gallery to help you get your design project started. Learn more at optics.ansys.com or scan the QR code on this slide. Be sure to check out our Ansys Innovation courses. These are free online physics and engineering courses that include videos, lectures, accompanying handouts, simulation exercises, and quizzes. Visit ansys.com/courses or scan the QR code on this slide to learn more. And finally, you can join the Ansys conversation. Sign up for our blog on Ansys.com and follow Ansys Optics on LinkedIn to keep up on all the latest Ansys updates. Thanks again for joining us, and have a great day.